I do want to go and back to the naming of the compounds, just so that I make sure that I have time for that before you guys leave today. So let's take a look at that real quick. So one of the first things on your guided notes was the naming of the hydrocarbons. And we said we use the prefixes meth, eth, prop, bute, and then we start getting into normal, pent, hex, etc. Based on the number of what? Carbon. Okay. Now, when we have only single bonds, then we call this an alkane, and the ending is in ane. So remember, our first one was CH4, which was methane, right? One carbon starts with meth, ends with ane. Okay, that should have been in your notes. All right, in your vocabulary, you had the term olefin. Anybody remember what an olefin was? Just wrote down the word and didn't really think about it. Okay. So if there are double bonds, and that's usually shown with what looks like an equal sign between the two carbons, then we call it an olefin or an alkene. Now, for some reason, your book really likes the term olefin, and it shows up in a couple of different chapters, which is why I have you do that as a vocabulary word. But for naming purposes, the ene is important. So with methane, we can't have a double bond between two carbons because we only have one carbon. But if I had a molecule with two carbons and a double bond, what prefix would I use for the two carbons? This was one, F, F for two. So we would call it F, and then just put E. We also talked about if we had an alcohol, which has the name hydroxyl. So in the assignment that you're going to do, it talks about there being a hydroxyl. That means there is this OH group, which is also called an alcohol group. Then we change the ending to OF. So we had CH3OH was methanol. And I guess we change it to anol, not just all. So let me do that. Propanol, octanol, yeah, they all have an ANOL. But they'll end with an OL. And the last thing that's going to help you with that is some different ways that we draw these compounds, because the carbons can kind of go in lots of different directions. And because there's lots of carbons, we have two ways that we might draw them that take a little bit less time. So I'm going to take pentene. So how many carbons am I going to have for pent? 5, like a pentagon. I'm going to put the double bond there. So this we would call the structure, right? It shows everything's connected together. But man, it just takes a long time to write that out. So one thing we do is called a line structure. So a line structure, can I erase this stuff up here? Everybody done with that? Okay. A line structure shows just the carbon-carbon bonds, and it shows them whether they're single or double. So I've only got one line here. So I would have one line here, a double line, one line, and that's not a line. So I'm going to have 1, 2, 3, 4 lines, one of which is going to be a double line. I'm not going to have any letters on here. And in order to keep it just from being like one straight line, what we do is we do up and down. So it's going to be line up, line down, line up, that is a double bond, and then a line down. So when you see a structure that looks like this, every corner and every end that doesn't have any letters on it is going to be a carbon. Every carbon is going to have 4 bonds, And so we just assume that if we're not showing the other bonds, those bonds are to hydrogen. So this carbon is this carbon here. We have one bond to a carbon, and that means the other three are to hydrogens. That's how you know how many hydrogens there are. Okay. I'm not going to make you go back and forth between those. What I want you to know is when you see structures that look like they have a bunch of zigzaggy lines or hexagons, that just means there's a bunch of carbons there. Okay. That's the key takeaway of that. The other way that we can do this is if I'm trying to show somebody what this structure is, but I don't have, like if I'm typing and I just am trying to write in a line and I don't want to draw a picture, I can group each carbon together. So I'm going to say this carbon, the first one, has 1, 2, 3 hydrogens. So I do CH3. The next carbon has 2 hydrogens, CH2. The next carbon has 1 hydrogen. And then if I want to emphasize there's a double bond, then I'll put an equal sign in there because I'm typing. Next carbon has 1 hydrogen, and the last carbon has 3 hydrogens. So this is called the condensed structure. So it is condensed from this big old thing to this. It's not quite as condensed as that, but you can tell how many carbons and hydrogens there are. Okay, so you will see in that assignment a reference to the condensed structure. This is what it's talking about. Okay. So I think that covers everything on those. So light is a kind of radiation. Radiation is what we call electromagnetic radiation. So it has electrical properties and it has magnetic properties. So basically, when you have any kind of a charge, say a positive charge from a proton, it's going to attract negative charges around it. And so it has this field, this area where it can attract things. Okay. So when it's a really strong attraction, it's high. Okay, that's this wave is being high. That's a strong attractive. And then when it's low, it's here. When it's repelling those things, so if it were a negative charge, it's down low. Okay. Magnetism would be like the north and south of a magnet. So it can repel one side of a magnet and attract another side of a magnet. And so that can go back and forth too. So light is these fields going back and forth, constantly changing. So I don't have just a proton there. I have something that is changing from positive to negative billions of times, more than billions. Well, billions of times per second. And it's also affecting magnetism. So light has those wave properties, can go up and down. It has a magnetic field. That's this red thing. And it has an electric field. And that means that I can produce electricity with a magnet, and I can produce magnetism with electricity. For our purposes, we don't really need to know what the electric and the magnet things are going on. We just have to believe in our heart of hearts and in our brain that light is doing this, and other forms of radiation do this as well. Okay, we talked already, put this in your notes, about the properties of waves. It has a wavelength, which we said could go from the top to the top or from the bottom to the bottom, and that we might have a different frequency because the different kinds of light all travel at the same speed. Okay, so we said C was the rate that they travel at. It's about 3 times 10 to the 8th meters per second. So that's 300,000 meters per second. So 300 million meters per second. Red light traveling at that speed has fewer waves, and blue light has more waves. Okay, so that's our frequencies, how many up and downs are going on. Red light is just moseying up and down. It's still going fast this way, but as far as the up and down, it's just moseying. Whereas blue light is going, whoa. Okay. We also talked about the amplitude. And we have these symbols. Remember, lambda looks like an upside down Y. That's the wavelength. The V is the Greek letter nu. That's our frequency. And that's just a number per second. And they all travel at that constant speed. That says depending on the medium. You might remember my saying it travels the speed of light in a vacuum, but the air isn't a whole lot different. And so we just kind of pretend like it's a vacuum. If it starts going through glass, if it starts going through water, it's going to slow down. Okay, so I said, believe in your heart of hearts that those waves are happening for visible light. So this is what we can see. Red to blue. The longer the wavelength, so this is a long wavelength here. So on the top, this is long wavelengths are on this end. The frequency is very small. So here we have 10 to the 4th, where here we have 10 to the 20th. High frequency goes with short, or high frequency goes with short wavelengths, short frequency goes with high wavelengths. Of all of this, they all are that same electromagnetic radiation. It's just different rates of those waves going back and forth. We can only see this. And that has to do with the way light interacts with matter. The changes that have to happen in our cells in order for our brains to process that information have to happen on that atomic level. And the changes are too subtle down here, and they would blow apart our cells up there. So we don't want to be looking at that stuff. And so we just have this narrow area where there's enough of a change that our brains can register it, but it's not harmful to us. So our cells have developed to highlight that. Okay. We said red is the longest wavelength and the lowest frequency. Energy goes along with frequency. So kind of hard to see the red there. The lower the frequency, the lower the energy. The higher the frequency, the higher the energy. Infrared is just on the other side of red, so it's even lower energy. And ultraviolet is even higher energy. So remember when we were using the ultraviolet light, we could get those to make the glow paper glow, to make the rocks fluoresce, those kinds of things, because they were high energy light. Whereas the red light didn't really do much other than we could use it as a laser pointer. Okay, so what kind of light is coming from the sun? Obviously, there is visible light, but that's a narrow part of the spectrum. So what ends up happening is that we're getting light from the sun because it's a big ball of fire. It's hot. We know hot things glow. If you turn a burner on your stove, it probably turns red. It might even get to yellow or orange or yellow, depending on how hot it is. So hot things glow. The sun is glowing. And it's giving off all of this radiation. This is the visible stuff. This is ultraviolet, and this is infrared, and probably down into some microwaves as well. We can only see this narrow portion of it. It turns out that what we can see is also the most intense light that's coming out. So this is how bright that light is. So you can think of the ultraviolet is a little dimmer, the infrared is a little bit dimmer. But when we think about the amount of light, because these are wider areas, we end up getting more of those other parts. So more than half of the light coming from the sun is infrared. And then a small portion is ultraviolet. Okay, so, and a good chunk of it is visible. All right, so what's going on when light interacts with matter? All right, you can tell these candles are still pretty new. So I haven't actually tried these. So I'm assuming they work the way that they are supposed to. But what happens when you light the two candles? So are your two flames different colors? Yeah. Okay. So that is the major thing that I am hoping to look at here. So on here, we can see two different color flames. So I will tell you, it doesn't come from like food coloring or dye. Those would just burn the same yellow or orange that we are used to. So we would have different colors on that. I mean, the same color on that rather than different colors on that. What we have is different metals in them. And it turns out that different elements are going to burn in different colors. And most of the time we're burning organic things. Carbon doesn't really have much of a color when it burns. But if you put sodium in it, it's going to burn yellow. And there is a ton of sodium in the environment. And if you put calcium in it, there's a bit of calcium around, especially in this area. We got lots of calcium in our rocks. It will burn orange. And so we're used to seeing things that are showing us the colors for sodium and for calcium. But different elements are going to burn in different colors. So we are going to look at that. Let's think about an atom. You may have in a high school or middle school class talked about Bohr's model of an atom. You may have looked at this model, but not called it Bohr's model. But this is how we kind of think of atoms, is there's a nucleus, that's where the protons and neutrons are, and then the electrons are on the outside. Thus far in this class, we just kind of left it at that. But our understanding is that those electrons don't all sit in the same place, and they don't all move everywhere. They have levels they're assigned to. So we have an inside level, think of like the inside of an onion or a head of lettuce or something, a very small level, and then layers on layers outside of that that are larger and larger. Okay, so those rings are our electron energy levels. And those are going to be important for how we understand light from our candles or from our laser pointers or whatever interacting with matter. So for each atom, there are two kinds of electrons. The ones that are on the inside are the core electrons. Those pretty much are stuck to the atom. They're close enough to the nucleus, which is positive, that they can't really get away from it. Okay, they're brainwashed by the nucleus to stay with that atom. The ones on the very outside layer are what we call valence electrons. And I just realized this illustration is done poorly. This is not a valence electron, but this one is. So that's on an inside layer, that's on an outside layer. These two are valence electrons. So the outermost layer, only the outside layer, is what we call valence electrons. The atom can lose those, or they can add to that layer so they can have more electrons in that layer. That's what we would call forming an ion. So when it gives up an electron or when it steals an electron, that's forming an ion. Or it can share those electrons. But another thing that can happen is when you put enough energy in, one of the core electrons can move outwards, but maybe not leave the atom altogether. Maybe it just has enough energy to get a little bit further out. That's what happens when atoms absorb light. So you might have heard that like dark colors like black will absorb more energy from light. More of those atoms are having their electrons move further away from the nucleus, but not far away enough to leave the nucleus. Okay, so our valence electrons are the outermost energy level. And those can be shared, which would be a covalent bond, or they can be gained or lost, forming an ion. Now, later in this chapter, we're going to be getting to drawing dot structures. So we're going to use dots to represent the electrons. Usually the atoms are most stable when that valence shell has 8 electrons in it. We consider that to be full. Hydrogen is, of course, our problem child, so it's going to be happiest with only 2, but we'll get to that later. Our core electrons are all of the energy levels, not just the very first one. All of the ones that accept the outside energy level are considered core. And those electrons stay on the atoms and not involved in chemical reactions. But if I have electricity, if I have fire, I might be able to get those electrons in the core to move outwards. If I have an X-ray, I might be able to get them to pop off altogether. X-rays are very high. All right, so you may start seeing our connection here. So we've said that color can be absorbed into the light and can cause the electrons to move around. We see fire here is one of the things that can move those inside electrons. And our candles had fire, of course. So we're going to have that fire move those core inside electrons. All right, so in the coming slides, I'm going to show you some animation. You're probably not going to be able to draw out all of the things that I'm showing you, but these slides are available on Canvas if you want to look at the animation. Here's an atom with its ring. So we only have 2 rings around it. Looks like it has 6 protons, so this is probably carbon. And if light comes in, it can hit one of those inside core electrons and cause it to move outward. So that is energy being absorbed by that carbon atom. But then what happens? What happens is that the electron really wants to be back close to the nucleus. And so it's going to fall back down. And when it falls back down, it's going to release that energy. Often it gets released as heat instead of as light. So changes happen to the light before the electron falls back down. And so things that are black or dark blue or whatever that have absorbed a lot of that light energy start to get hot because the light energy is turned into heat energy. Now, if I have a fire like our candles, or if I have an X-ray, then what can happen is that I have enough energy that is absorbed that when that core electron gets hit, it flies off altogether. This is particularly true of X-rays. All right, so our flame might have electrons that are being pulled out of it, and they're probably running into other molecules in the air around it and, being neutralized. But then what happens? Well, that electron's not close enough to fall back down, but there's a hole under it, right? So if you play Jenga and you pull blocks out of the bottom, eventually you're going to get to the point where there's not enough support and the blocks on top want to fall back down. So these outside electrons are going to fall back into that place. As they do that, they're going to let off energy, but that energy is much less energy than the X-ray or the heat that expelled it in the first place. That energy is going to be in the visible light. And so we're going to see a color coming out as that electron goes down. Okay. So depending on what element we have there, whether it is potassium or barium or lithium, the spacing between these energy levels, the amount of energy between these is going to vary, and we'll get different colors. So for lithium, the area between those colors is right about the right to give kind of a magenta color, a dark red. And for strontium, it's a little bit more, and so it's kind of an orangey red. And then if we have sodium, or calcium is a little bit more than that, so it's orange. And then sodium's a little bit more than that, and so it's yellow. Barium is a little bit more than that, so we get green. Copper, a little bit more than that, so we get blue. Sulfur is also in that blue range. And the one that's the largest would be purple, and that's potassium. But potassium actually has a couple of different colors, so you get kind of a pink and a purple at the same time. So we get a mix in there. So that's how we get our different colors from our flame test or X-ray. See, I'm not sure why I have this already in here. Oh, this is showing why potassium can have two different colors because it depends on where it comes from. So potassium might have the pink color coming from this one falling down, or the purple color coming from this one falling down. Okay, we also talked about phosphorescence or fluorescence. And this kind of goes back to the idea that we said with the heat and dark things, that as they absorb that light, your shirt that's black doesn't start suddenly radiating light, it just gets hot. So internal changes happen in the atom when the light hits it. So when visible light hits it, it downgrades to a lower energy, which is heat. But if I have ultraviolet light hitting these things, it's going to downgrade into something that is visible. And depending on how long it takes for that to happen, we call it fluorescence or phosphorescence. So we still have the same process going on, but first we have the electron move from this ring to this ring, and then it falls all the way down. And that's why we get a different color. We still got 2 minutes here, guys. I know the cat food isn't that great. All right. Let's see. We looked at, you don't have to worry about writing this stuff down, but we looked at different kinds of light, and I gave you those beads. Did anybody try out the beads at different times of day or under cloudy days or sunny days? See different colors you could, or not different colors, but whether or not they changed? All right, so on a bright day, you got a big intense color change, and it doesn't take long for it to happen. If you go outside right now and you have those beads out, they're going to change pretty quickly. But on a cloudy day or at the end of the day, when the light is very low in the sky and there's not a lot of radiation, it's a slower change. Okay, so it has to do with how much the intensity of that light. Now, when light hits something, three things can happen. It can be reflected. So white tends to reflect all of the light. And so pretty much any light that is in this room is going to bounce off and we're going to see it. So a lot of times people will paint rooms where they have, they do a lot of their living during the day, or they invite guests to, they'll paint them light colors. So it'll seem very bright in there. And then you might use darker rooms for like bedrooms or for a den where you might want to have more of that calming, darker, or maybe romantic atmosphere. So it gets reflected, it can get absorbed, and we talked about what happens with that. And then if you have something that's clear, it can get transmitted through. So you need to know those three terms. Now, sometimes two of those things can happen at the same time or all three. So if you've ever had sunglasses that are like mirrored, you know that some of the light gets through because you can see, but it also is reflective and they also get warm in the sun. So all three of those things are happening at the same time. Different colors occur because of which wavelengths are absorbed. So I said white light, we're going to reflect all of it. Black things absorb all of the colors, and basically we're not reflecting anything. Now you are reflecting a little bit of stuff unless you have something called Vanta black, which basically absorbs everything. It's kind of creepy to look at because it's like there's a hole there. But if I'm looking at something that's yellow, what could be happening is it's absorbing everything except for the yellow. So only yellow is reflected. That would be a dark yellow because I get very little light coming off. Or a lighter yellow might be occurring because I am absorbing the blue or the purple. The yellow is coming off, and so are some other colors that are kind of canceling each other out. So this color wheel, the things that are opposite one another tend to cancel each other out. So red and green, if they both appear at the same time, they look white or very pale yellow. And so we might just think of that as being yellow. If I have blue and orange, again, they're going to kind of cancel each other out. And purple and light green or purple and yellow can kind of cancel each other out as well. So when I see a color like this green thing here, I'm definitely getting the green reflected off of it, but because it is a light green, I'm probably getting a little bit of all of the colors except for red, probably absorbing most of the red. Okay. All right. I will see you all on Thursday. Don't forget to do your assignment online. I think I forgot.